Alright, so here is a harder problem, and it involves us using a major concept in physics and even chemistry, and that is the law of conservation of energy. And basically, the law is just what it sounds like, that energy is conserved. And this is the case here. We've talked about two types of energy so far, kinetic energy and potential energy. And the idea is unless there are outside forces at work, an object's total energy or mechanical energy does not change. Now, it's true that a lot of times you can't keep outside forces from acting on it, so it may decrease a little bit. But for many problems, we're going to assume that the energy before and the energy after is the same. And that's how this type of problem is done. So what we can do is basically make a column, and the left column will be our before, and the right column will be our after. And so what we're going to do for each column is we're going to write how much energy it has. So before, how much kinetic energy does it have? How much potential energy does it have? And how much mechanical energy does it have? Same thing after. Kinetic, potential, mechanical. So we just got to make these calculations, calculate as many as we can. So we know the mass of the ball, and that's not going to change before or after. And it's initially held at 20 meters. So if we know it's at a height of 20 meters and its mass, we can calculate the potential energy of the ball, because that equals the mass times g, 10, times the height, 20. So the potential energy of the ball before it's dropped is 5 times 10 times 20, or 1,000 joules. And so I can fill that into my chart. Now, it's being held at this height, so that usually means it's not moving. And remember, kinetic energy was 1/2 mv squared. So if it's not moving, its kinetic energy before is 0 joules. So that's its kinetic before, that's its potential before. So the total amount of mechanical energy it has before is 1,000 joules, because mechanical is potential plus kinetic. Now, according to this law of conservation of energy, any energy I had before, the total, should equal the same amount after. So that means there is 1,000 joules of mechanical energy at the end. And so I write that down. Now it wants to know its speed just before it hits the ground. So we're not given really much more information, if you look at the problem, to calculate potential or kinetic at the moment, if we think about it. In order to find out its speed, we're going to have to know its kinetic energy. You may say, well, how do we know that? Well, if it's just before it hits the ground, we can assume that the height of the ball after is 0. So that means the potential energy of the ball, just as it's hitting the ground, is also 0 joules. And you can see the chart, this makes it hopefully a little more visual. If you have a total of 1,000 joules after, and none of that is potential, then all of it must be kinetic energy. So there is 1,000 joules of kinetic energy after, just as it's hitting the ground. And now we can treat this just as solving a kinetic energy problem. We're trying to find the velocity, or the speed, right before it hits the ground. So we know the mass is still 5 kilograms, and we're looking for V. So it's, again, kinetic energy 1,000 equals 1/2 times m, 5, times v squared. And then we just go through. I'm going to kind of save the steps because we've done it in a previous problem. We're just going to solve for v. And when I solve for v here, I get that it is 20 meters per second. So that's how fast the ball is going when it hits the ground. Now I can double check that. Does this velocity actually give me a kinetic energy of 1,000 joules? And if I go through and plug in all the numbers, I would find that it does. So that is the answer to this type of problem, and it's all done with this chart. Now there's algebraic ways to do this all in one step, but I think conceptually this is a good way to start to get yourself understanding what's going on with the process. Here's another problem that we can solve in the same sort of manner. We'll make a chart before and after. And we're just going to analyze the energy at each point, both before and after. So we've got kinetic energy before, potential energy before, mechanical, kinetic energy after, potential energy after, mechanical energy after. And we're going to figure out as much as we can about this. So the roller coaster starts off at a certain height, and it doesn't tell us the mass. That's one thing you might notice right away it seems to be missing. Well, if they do not tell you the mass, you can actually assume really any mass you want, because ultimately it's going to cancel out in the problem. It won't matter. So for the purposes of this, I'm just going to say the mass is 100 kilograms, and we're going to use that for the entire problem. So if you know the height of the cart, then you can calculate the potential energy of the cart, because the potential energy is mass times g times h, and so we can just calculate that. So 100 times 10 times 50, and that will be 50,000 joules. And so we can write that down. It's also moving at a speed of 10 meters per second, so we can get the kinetic energy, 1/2 times 100 times v squared, and so 100 times 100 times 0.5, there's 5,000 joules of kinetic energy, which means the mechanical energy is 55,000 joules, both before and after, due to this law of conservation of energy. Now it then wants to know how high above the ground will it be when it is traveling 25 meters per second. Well, if we know the speed after, we can now calculate the new kinetic energy, 1/2 times 100 times 25 squared, and so we can calculate the kinetic energy at this point, and that is going to end up being 31,250 joules. So if that's the kinetic energy and we know the total energy, you can find the potential energy by taking the difference, because the kinetic and the potential must add up to that 55,000. So the potential energy is 23,750 joules. But that's not the final answer. We're looking for how high above the ground it is. So remember that this equals mgh. So 23,750 equals 100 times 10 times h. And solving for h, we will get that it is 23.75 meters above the ground. And again, that's sort of the way we go about this. So if you're making a chart, you're keeping track of all your information, I think conceptually you'll understand this better, and you should do all right. And does this answer make sense? We started at a height of 50 meters, and now we're at a lower height, and we're going faster. That should make sense, because we converted some of our height, or potential energy, into speed, or kinetic energy. So if this were higher than 50, then that wouldn't make any sense. There's no way you can go higher and gain speed without gaining energy. So, always look at it, make sure it sort of makes sense. So that's it. Until next time, I am Derek Genova. Have a delightful day.